Alright, we've got our last video for our rational roots. So we're going to use the rational root theorem to find any rational roots. If we find one, we will solve it completely. So, looking at our example, we're going to take factors of our constant, which is 15, or negative 15, and we're going to divide it by factors of our leading term, which is just a 1. So plus or minus, because you can have positive and negative factors. Factors of 15 are 1, 3, 5, and 15. And just to check, 1 times 15, 3 times 5, all over 1. So a positive or negative 1, 3, 5, or 15. So we use our synthetic division to check all those, or just go until we can find one that works and is a factor. So let's try 1 first. We write our coefficients up here. The coefficient of x to the 4th is 1. And then notice we're missing our x cubed. So we're going to do 0 for x cubed. We have a negative 2 for our x squared, then a negative 16 for our x, and a negative 15 for our constant. Alright, then we do our synthetic division. We add down, and then we multiply. Add down, multiply, add down, multiply, add down, multiply, add down. We got a remainder, so it did not work. So we move on to the next one. Let's try 3. 1, 0, negative 2, negative 16, negative 15. Add down, multiply, add down, multiply, add down, multiply, add down. Oops, that's going to be a positive 5. Multiply, add down. Alright, we got a remainder of 0. That's a good thing. That means we found one of our roots. X equals 3. So, here's our constant, here's our x squared, and here's our x cubed. So the issue here is that our remaining polynomial, when we divide it by that 3, we get x cubed plus 3x squared plus 7x plus 5. That is not a quadratic, so we can't use the quadratic formula. We can't factor and solve. So what we're going to do is we are going to now use the rational roots theorem again. We're looking at factors of 5 over factors of 1. Well, that's just positive, negative 1 and 5 over, oops, not 5, over 1. So our possible factors we're going to try are a 1 and a 5, because 1 divided by 1 is 1, 5 divided by 1 is 5. Alright, so we give this a try with our synthetic. We'll try 1 first, where we start at the beginning of our little list. Our coefficients of our polynomial are 1, 3, 7, and 5. Alright, so we add down, multiply, add down, multiply, add down, multiply, add down. We did not get we got a remainder. So let's move on to 5. Alright, 1, 3, 7, 5. Add down, multiply, add down, multiply, add down, multiply, add down. We got a remainder. Alright, so this is actually good that this happened, because now we've tried the positive 1 and positive 5, so now we need to try the negatives. Let's see if negative 1 works. And sometimes you just have to go through all this And as long as you're being careful with your synthetic, it won't be that bad. So I added down, I multiplied, add down, multiply, add down, multiply, add down. All right. So we got a 0 remainder, which means we got something to work out. So you see how we said that x equals 3? Well, x also equals a -1. We just found 2 roots. We did have to use the rational root theorem twice for that to work out. So now let's look at what we have. Here's our constant, here's our x squared. So 1x squared plus 2x plus 5. Are there factors of 5 that add up to 2? No, there's not. So you can use the quadratic formula. You can complete the square and solve, whatever's easiest for you. Maybe I'll complete the square just to keep that in our heads again. So that's the one where you do x squared plus 2x, you put in your spaces, plus 5. Remember how we would take 2 over 2 and we square it. So add in a 1, subtract a 1. This factors into x plus 1 squared. -1 plus 5 is a +4, and this all equals 0. And now we're just solving the equation. So we subtract 4 from both sides. X plus 1 squared equals -4. Square root both sides. So x plus 1 equals, now this is an I square root of 4, which is just 2i's, but positive and negative because we square rooted, so 2i. Go and subtract 1 from both sides, so -1 plus or minus 2i. So if we go to our list of answers that I had up here somewhere, oh there it is, we can now add in -1 plus or minus 2i. So really we have 4 roots or 4 zeros or 4 answers that we found for x. 3, -1, and then this is actually 2 answers. It's a -1 plus 2i and a -1 minus 2i. So sorry that one was as long as it was, but we did have to do the rational roots theorem twice, which is good to see. Good example.